Hello, and welcome to episode 3 of Causal Foundations. My name is Naftali Weinberger, and in this video, I'll explain how to identify causal effects without experimentally intervening. I want to begin with a question that perhaps you've already been wondering about. Namely, what should an account of causation do? For many philosophers, the goal is to replace causal concepts with some more basic concepts, so that you could explain it even to an alien who had no causal knowledge. For others, the aim is to systematize our intuitions about increasingly convoluted thought experiments in which people make judgments about what caused an event. For me, one of the most basic criteria for evaluating a causal theory is whether it gives a general analysis of how to eliminate confounding. Without such an account, we couldn't know, even in principle, how to measure causal relationships in the world. The analysis of confounding I present today clarifies how it's possible to measure the magnitude of a causal effect, even in cases where one does not experimentally intervene. Experimental interventions are the most uncontroversial way to eliminate confounding. By beginning my discussion with contexts in which one does not intervene, I'm going a bit against the philosophical grain. In recent years, the notion of an intervention has become central to philosophical discussions of causation, largely due to Jim Woodward's interventionist account of causation. Woodward has single-handedly improved the scientific rigor of philosophical discussions of causation. Now, nothing I say in today's video is intended as a critique of Woodward. Some of my best friends are Woodward. But my impression is that philosophers who read Woodward without a more general understanding of confounding fail to see how interventions fit into the more general inferential framework. Today I'm going to try and fix that. To begin, consider this causal model. In it, a drug influences one's risk of heart disease, but whether one takes the drug is also influenced by some other factors such as gender, which also influences heart disease. Broadly speaking, in causal inference, we're trying to disentangle between two ways in which the drug might provide information about heart disease. Either, 1, the drug can causally influence heart disease, or 2, learning that someone took the drug may merely provide evidence of their gender, and thus of their baseline probability of getting heart disease, whether or not they take the drug. As you may know, a common way of disentangling between these is by intervening on the drug, that is, by randomly assigning individuals to take the drug so that their taking the drug is uncorrelated with gender. Such interventions are sometimes represented as breaking the arrows into the intervened upon variable. We denote interventions on X with the notation do X, where the probability of Y given do X corresponds to the probability distribution of Y given interventions on X. As we'll see, in cases with confounding, this distribution does not equal the observational distribution, the probability of Y given X. Over the course of this series, I'll have a ton to say about the notion of an intervention and its central role in causal inference. In today's video, we'll be focusing on contexts where one does not intervene on the variable of interest. The do notation will nevertheless be relevant for defining causal effects. The causal effect of X and Y can be read off of the interventional distribution, Y given do X. The most common effect measure is the mean difference, which is the difference between the average values of the effect given two distinct values of the treatment, though there exist other versions as well. At this point you may be wondering, how is it possible to learn a causal effect without intervening? To answer this question, you need only the tools that have already been provided in the last video. There we discussed the notion of deseparation, which allows one to precisely define the conditions under which a path transmits probabilistic dependence. Don't worry if you haven't watched that video yet. The key points are that a path is a series of connected arrows, and that one way to stop a path from transmitting probabilistic dependence is by conditioning on a common cause along that path. Let's refer to paths in which all arrows go in the same direction as causal paths. One way of identifying a causal effect is to allow probabilistic dependence to be transmitted via all causal paths, while not allowing it to be transmitted via any non-causal paths. So in this diagram, one would identify the effect by conditioning on x3, but not x1 or x2. Additionally, if there's a path such as the one through x4, one should not condition on x4 alone, since conditioning on a common effect can deconnect a path. This illustrates that it's not always a good idea to condition on added variables, even if they're before the cause. We can make this all more precise using the backdoor criterion, which will apply to the simple example we started with. A set of variables z satisfies the backdoor criterion relative to x and y if and only if 1. No node in z is a descendant of x, so this means that z is not an effect of x along a causal path, and 2. Z blocks every path between x and y that contains an arrow into y, where blocking just means deseparating along a path. Here we can easily see that there is only one such path, and it is blocked by z, so z satisfies the backdoor criterion. When z satisfies the backdoor criterion, one can identify the effect via backdoor adjustment. This says that the effect of x and y can be derived as a weighted average of the probabilities of heart disease given the drug in the male and female populations, weighted by the sizes of those populations. I'll say a lot more about this in the next episode. In this example, we say that the probabilistic formula on the right-hand side identifies the causal effect. I can now present what I take to be the most underrated concept in causal inference: causal identifiability. Identifiability concerns whether, given one's causal assumptions, one can in principle measure a causal effect from data. More precisely, given 1. A causal graph, 2. A probability distribution indicating the dependencies among the variables in the graph, and 3. A causal effect, the effect is identifiable from a probability distribution if and only if it can be uniquely determined from the distribution. The easiest way to get a feel for this is to give an example where the effect is not identifiable. If there is an unmeasured common cause of x and y, the effect is not identified, since no matter how much data you collect, you can't know how much any of the correlation between x and y is due to the causal relationship as opposed to the common cause. In contrast, if there were to be no common causes or other confounders, the effect would be straightforwardly identified. Finally, when there's a single and complete common cause that one can measure, one can identify the effect using the backdoor criterion. The backdoor criterion is only a sufficient condition for identifiability, but Pearl's do calculus gives a sound and complete procedure for identification. When an effect is identified without interventions, it lets one determine how the effect would respond to interventions on the cause, even without physically intervening. The advantage of intervening is that, by breaking the arrows into the cause, it allows one to identify an effect, even in cases where one cannot measure all confounders. Since the expression do x can be understood as a form of idealized intervention, the picture presented here still allows interventions to play a central role. But there's nothing magical about physically intervening. What matters for causal inference is that one can identify the causal effect, whether through observational or experimental studies. I'll conclude with a few unresolved debates regarding the relationship between causation and interventions. There are several debates about whether causes must be manipulable, where manipulation is roughly synonymous with intervention. Some of these debates have to do with the empirical question of how confident we should be when inferring causes from experimental as opposed to observational contexts. The answer to this question depends on the reliability of our knowledge in particular domains, and is not settled by anything I've said here. Other debates have to do with whether causal variables should be defined as linked to particular interventions, or as linked to data-generating variables that might be intervened upon in multiple ways. We'll get to this in later videos when I discuss causal graphs versus potential outcomes. Finally, there's the philosophical question of whether there are causes that don't allow for even hypothetical manipulations. This question is unresolved, but the discussion here sets the contours of the debate. Pearl, The most prominent advocate that causation does not require manipulation still maintains that in order for X to be a cause, do X must be well defined. We've seen that it can be, even without physically intervening. But the question remains open: are there any examples in which do X is well defined, but where we can't imagine even a hypothetical manipulation? To me, this remains an open question, which I'll return to in a future episode. While you ponder this further, consider an example that Pearl posed to me when I talked with him about this. The moon causes the tides, but can we imagine an intervention on the moon? Thank you for listening. For further reading on identifiability, check out Felix Elworth's chapter in the Handbook of Causal Analysis for Social Research.